class stuff. So for anybody at home, sorry you're sick. Feel better. Please and thank you. We today are starting chapter 4, and as you guys voted yesterday, we are going to take your mastery, start it on Thursday, and then finish on Friday. If we have time on Friday, we will also then start something else or do something else. So your homework today is 6 through 10, so please make sure that is in your plain book, because I did not have the other homeworks up there. Then tomorrow's, if you want to go ahead and write it down, it's 16 through 20. Now the chapter 3 homeworks will be collected on Thursday. So, now I don't normally say this. I'm scared to say this. I get scared easily. I might be loud, but I have lots of fears. I used to be afraid of heights until I started rock climbing. I don't like spiders either. I don't kill them, but I'm afraid of them. They eat bugs, which is good. If your chapter 3 work is done, and this is really gonna did I collect any chapter 3 yet? I didn't think so. I did this on purpose because, especially with this class, that's just how it's gonna roll sometimes. If there were any other chapter 2, we merged chapter 2 and 3, we're taking one test. I just care to see your chapter 3 work. So, if you want to look in your binder, with me real quick for a moment, what I would be expecting you to turn in goes back to September 13th, and it's 321, 322, and 323, but there was a merged homework in there. So 321 and 322 was a merged combined homework. So you probably only have one homework with both 321 and 322. Then 323 is its own homework, and I'm not going to go over the questions because you guys should have those. 324 and 325. Then 331, 332, 333. That's it. Nothing from chapter 2. I don't care to collect those. I just decided I'm going to cut it. What? Hang on to them for now. We're going to talk about your student portfolio soon. I forget if I've announced this in the class. I need to just go ahead and one of us teachers every year makes you guys little hanging folders to put in a filing cabinet, and we give you guys drawers so you can keep your work that you pull out of your binder in there. I would not advise recycling or throwing anything away yet because we have student conferences later in the year that it's good to be able to pull out any old work, even if you didn't care about it at that current moment. So really, if we count them up, then it's 7 homeworks. 3, 2, 1, 2, and I'll have them listed tomorrow. On Thursday. I'll list them tomorrow so you can double check. And then on Thursday, I might even write them on the chalkboard above the turn-in bin. So here's what I'm really saying. Whenever you're ready to turn those in, you can go ahead and turn them in. So don't rush my bin right now, but at the end of class, if we have some time, which we probably will, you can go ahead and turn those homeworks in. Or AO, extensions, whenever you get those all wrapped up, just go ahead and get them turned in. I'm not checking them until Thursday. I'll probably check your homeworks while you're taking your test. Quite honestly, I'll double dip on that time. I don't think I have anything else. Anybody have anything else? Any announcements? Anything for the good of the order? Yeah. Yeah, that's all. So, the question was asked over there, can we go ahead and recycle those or whatever? Hang on them for now, and I'll try to make this happen this week. We're going to give you hanging folders to put your stuff in the filing cabinet as opposed to keep it in your binder long term. But don't just get rid of it right now. I just decided chapter 3 had no other content I really cared to look at your practice on, and I don't want you turning in a giant stack of work. But then what that also means is if you have a test revision that you're turning in, if I'm at my desk, you might want to be hey, this is a test revision. Do you want it, or do you want me to put it in the bin? And then at least I know if you put it in the bin, I'm aware of it. And if I'm able to, I'll just grade it right then. I'll talk to you about it, grade it right then, and get your grade changed. Today we start talking about similar figures. Anyone know what similar figures means? sorry, before we dive in this, does anyone have any chapter 3 homework that you're wanting to ask questions on? I should have asked that before, but anything that you're like, oh yeah, the whole class is probably having issues on this because it was like a foreign language to me.
I have my own issues, but that's because I have my own issues because not because of the homework, but because I didn't do it because I thought I already had it because I did my notes on the homework.
So that's an organization thing. Yeah, so we can work on that. Come meet with me if you want to create like a plan or something.
No, I just need to do it. I crossed out notes for the previous one since there's nothing on my notes.
Similar figures. Okay, what's a figure? Then if no one's going to take a stab at what similar figures are. Now, not like figure this out, but Simon?
Like a picture or shape.
Yeah, it's a thing.
Similar figures would be ones that are either the same or alike.
Ooh, now I like what you just said. It's either the same or alike. Now, if it's not the same, how might it be different, but still similar? Actually, let's go Savannah. We'll alternate gender.
Like the shape of it could be similar, or like the design.
So what do you mean the shape could be similar? Like, is the shape going to be the same, or is the shape going to change? Like, if I start with a circle, am I going to change into a square? Call that a similar figure. George?
So it's like enlarging or like having the same. It's like it's like making everything bigger or everything smaller. Like I don't know how to explain it that well. Yeah, like reducing and enlarging the shape.
Who's ever done this? Your computer glitches out. So you insert something into a dock, and then you grab one of these guys, and you do this. That is what we, in mathematics, call a dilation. Now, the dangerous thing with our computers these days is if I force this drag, sorry, I gotta grab a different handle, not from a corner, but from the bottom. And I just do this. Does that look the same? I did think it would be ironic to use the image from, but this is really funny because it says, are the figures the same shape? Yeah, so I'm having fun with this. This doesn't look right, right? And likewise, if I do that, it totally doesn't look right. It's like you're at a bad eye test. So, similar figures. Let's just go ahead and get like a definition on our page. So I'll pull my notes up. I'll actually toggle screens here real quick. I wish I had a hotkey that could swap what was on my monitor left and monitor right. So if you are like me and you want to make a little indication for definition off to the side. My computer's running slow today. Similar figures. Same shape. It's got to be the same exact shape. Different size. And here's the other kicker that I'll give you guys because you're the advanced class. All angles preserved. Which is this cool thing about angles. Right? If I look at a railroad intersection and I only look a meter in both directions, I can find the angle of those tracks. Right? I've got a meter this way and one, okay, I measure. And if you know much about angles, you can also find like vertical angles will be identical to each other in different relationships like that. I should draw this so you guys know what I mean. So if I take this triangle and say, if I'm trying to guess, maybe this is 50, This is 40. Now this is going to get screwed up since I picked up my pen. Oh, where's the other pen? It's in my pocket. So I grab that triangle, and right angles we can kind of tell, look right. They look like a corner. Are my angles still 40, 50, and 90? Yeah. Are my angles still 40 and 50 and 90? Yeah, so it doesn't matter how big the shape is, the angles get preserved. Now, the lengths do not get preserved. So how we talk about the lengths not being preserved, and I'll just give you, this is still another definition, so we can just continue on. We utilize a thing, I'm digging purple today, I should really be nicer, called a scale factor. Now, the scale factor is just a multiplier to, and you're going to have to get with me on math terms here. It's a multiplier to your linear dimensions. Linear just meaning the lengths of the lines, right? The side measures. And the reason that I specifically say linear dimensions is it does not work for area. And I will explain why. I like that we have a textbook, but some days it's like, I just want to teach you what I want to teach you. Now, I actually should have done that. So we have a square, start 2 by 2, right? If I utilize a scale factor of, let's say, 3, that would mean I multiply my linear dimensions by 3. Well, what are my linear dimensions going to become then? Yeah, well, 2 times 3, right, is 6. So, it broke. No, I got it. Here we go. So now my dimensions are 6, right? What was my original area when I had, and I'll even draw it again like on the inside here. So my original, right? I had my 2 by 2. And my area was 4. Now, with a multiplier of 3, sorry, I don't want a 3 there. I want a times 3 over here. Times 3. I got 6. What's 6 times 6?
36.
Is 36 3 times my original area?
No.
Now, I'll go even deeper to something you don't need to know right now. The area multiplier ends up being your scale factor squared. Our scale factor here was 3. What we do to the area is times 3 squared. What's 3 squared? 9. What's 4 times 9? You know how this works? Area, hold up. Area is to length by the square relationship. Right now, other figures get a bit more complicated, but looking at this with a square is really easy because my original is S, and this is 3S, right? My original area was S squared, right? The side length times the side length. My new area, you don't need to know all this. I'm just kind of teaching above to get you guys interested. Is my length 3S squared? But 3 gets squared also, so my new area is 9 times the S squared. And the S squared is that original area. That's how we get that cool relationship. Excuse me, but the biggest thing I wanted you to know is the multiplier works for lengths, not for area. You can make it work for area, but you have to square it. Questions? circles get really fun in doing this too because every circle is similar. If you think about that idea for a moment, it's kind of crazy. Like every square is similar. Every rectangle? No way. Every octagon? Yeah. If it keeps the rules of an octagon. Okay. Every regular octagon. Sorry, regular means all the side lengths are the same. So you can make an octagon that looks really awkward, but like if you think of the stop sign octagon, right? That's a regular octagon because all the side lengths are the same. Shrink it down, scale it up. They're all going to be similar to each other. But rectangles all have their own dimensions. They're all kind of crazy, whatever. I need to get back on the textbook and teach what I'm supposed to teach. Oh, we covered that. So, hopefully you guys are all using graph paper. Let's go ahead and copy down this shape. I'm going to get to my new page. So, the bottom of it is 2. It's 1 tall on the left. Now don't worry, I'm not going to cheat on this one. I'll do it just like you guys. Now you decide where you want to draw it. You could draw your new one surrounding your old one. You could draw your new one off to the side of your old one. But we are going to use a scale factor here. And sometimes scale factors are given as percentages because if you used a copy machine or something like that, you would need to know what percent. So what percent gets you your original back? 100, right? 100% is your original. So I set my scale factor at 100%. Well, that does nothing. Less than 100 shrinks it down. More than 100 makes it bigger. What's 300% going to do? Triple, right? 3 times. So make your new figure with the scale factor 300% of your original.
It is very thick.
Now, diagonal lengths are something that's really, really confusing. You do not have to know how to work with them yet. But if you want to know the length of a diagonal from one corner to the next corner, like what we have there, it is the radical, sorry, it's a D, not a T, radical 2. And we'll get into why later in the year. It really goes back to the Pythagorean theorem and how right triangles work together. But then we want to check, did I triple every dimension? So 1 should become 3. 2s should become 6s. My square root of 2 now actually becomes, well, it should be 3 times the square root of 2. So hopefully that works out because you guys aren't there yet. You don't even know how to calculate that. But if we just triple, it's going to be 3 times whatever we had before. Right? So we could write 3 square root 2. This should be 3, this should be 3, this should be 3. If we've done everything correctly, we're good. Scale factor of 300%. And we could also just say 3. If you want to work not in percentages, but in just decimal values, whole numbers. Yeah. Did you dilate out from the center? Is that the one you're talking about? What is it? And keep going.
We did SpongeBob.
Yeah, we did SpongeBob.
Yeah, I was gonna be kind of evil and say, now what about a scale factor of 1/2? But that shape's kind of too small to start, especially if we're working on small graph paper. Sorry, more vocab, just to make sure we talk about it. Corresponding means they're in the same location. So corresponding points get labeled using a special type of label. Now, this doesn't always happen, especially in CPM. They might call the first one like TRAP if it's a trapezoid, and then they call the next one like, I don't know, ABCD, something like. But if we want to use the corresponding notation, if I label these like A, B, C, D, E, and F, and then there'd really be like a G there, then these points, who knows how to make it corresponding but new notation? It's the image. So this now was the pre-image. This is weird, but the pre-image is what you start with. The image is what you end up with. Pre-image, image. Any guesses?
Why isn't it image or first image?
I know. I didn't make the rules.
Would you turn them into handles? No.
A is still A, but now it's A prime. We use what's called prime notation. So you want to write down a couple of these, please. By putting an apostrophe in the upper corner of it, that means, hey, it's doing the same thing as the original A or B or C. However, it's in a new shape. Any questions about that? Because then if I modify this shape again, I say then do da 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 da, it becomes a double prime, B double prime. And we can do this as many times as we want. So then you could have a triple primes or quadruple primes. Then it gets complicated. I've never seen anything beyond a quadruple prime. Because what it was take this shape and translate it. Draw it. Then dilate it. Draw it. Then rotate it. Or reflect it. And then rotate it. And like we did 4 different things. And it was like every time we just added a prime. Yeah. So, but I mean, you can put as many primes as you want. Any questions about notation? Yeah.
Just a small comment. I'm pretty sure with the Rubik's, I just connected this with a Rubik's cube.
Okay.
When you did Rubik's cube language has for like when you do like say F prime, you turn the front of the Rubik's cube like reverse it from your last move.
Okay.
Kind of Rubik's cube language. I just kind of I don't know connected with that.
I would challenge you, or more so encourage you, to write that out in a way that somebody who's not familiar with the Rubik's Cube stuff might understand it. Like, I don't quite get what you're saying right now, but I have resisted. Like, I know that there's a formal algorithm for the Rubik's Cube, and I used to, like, know parts of it, but I intentionally don't use that because I just like the joy, like, yeah, just try to solve it. But if you were to write that out, that'd be really interesting to test it. Like, is that actually... Like, can we make that relationship? Can we make, like, a rule?
If you are able to get 3 sides of the Rubik's Cube the same, then
Yeah.
it would already be the same.
Okay. The other way is if you are asked, sorry, not the other way, other piece of information I need to drop with you before we can really utilize this. If you've been asked to figure out the scale factor, that, and this is why I'm not using a colon, I'm using an equals, because now we're talking about the math. I'm not defining things. I'm giving you math. If you want to figure out the scale factor, you just take... Now, I don't like this notation, so actually don't write this for a moment if you don't want to. You could instead label this as image over pre-image. If you want to start doing your future self favors, I teach the high school math. Right? I know where you're headed. In high school math, we call it the pre-image and the image. The image is the new one. So if you write it down as that, you might notate that's new and this is the old or the original. Pre-image is where we start, image is where we end. If you are a brain like me, that bothers you, but I can't change it. So it's not my rule. That's like me wanting to change 2 plus 2. Not within my power. Yeah.
There's things like image and image because like it's the original then That's the shape it's gonna have. So
Yeah.
that's gonna be the actual image.
Yeah, no, Connor's got it. Like, and I just like kind of being a little goofy with math sometimes. But the reason it's called image is it's the thing we want to end up with. I want the image. I have to start somewhere. So the image is my end result, the thing I wanted to make. This one. This is fun. We have graph paper. Let's draw this one. Now this one, I'm going to encourage us to do the dilation very specifically. So just draw the original, then we'll talk together. Yep. Now it will help you to give some labels to your sides, length labels. We're going to do the new one inside of it, so don't worry about writing on the outside. A squared plus b squared, 4 and 4 is 8 squared of 8. It's really annoying to calculate diagonal distances until you understand it, and then it's really easy. For those of you who like me teaching above where you're at, really quickly, the way we get square root of 8 is I set up a right triangle, and the length of the diagonal of the right triangle is the square root of a squared plus b squared. So I take my a of 2 and my b of 2. 2 squared is 4. 2 squared is 4. 4 and 4 is 8. That's how I get radical 8. So I take the leg lengths of the right triangle, square both of them. I get 4 and 4 here because they're both 2. Add them together, and then just put that under the radical symbol. So that's how this length is radical 8. Yeah, so some people will be like, oh, it's 2 diagonal. Well, yeah, but that's not the same as 1 horizontal. Like, so that's what it is in actual units. Now, if you want to dilate this by a scale factor of 50%, what does that mean is going to happen as your multiplier? 1/2, right? Savannah's got it. So whether you use 0.5 or the fraction 1/2, so we can make this look really pretty. What? Certain things are pretty. If I want to make this really nice, I start it right here. Have a top of 1 because then I drop down by 2. And then I go diagonal, only 1 diagonal, and we'll figure out the length of that if we need to. Then I go over just 2, up just 1, over just 1, up just 1, over just 1, and up just 1. And you could, if you want to make your vision easy, shade the new one inside. Now you can just start to memorize these if you want. The distance of a diagonal 1 is the square root of 2. Now, you don't have to. I just I have made it a goal this year. I'll just be outright forward with you guys. I've made it a goal this year for you to leave my class with not just the knowledge that you should have, but other various knowledge that you pick up based off what you're interested in. So if triangles are interesting to you, this might be like, oh, that's how that works. Oh, that's what I like. And if not, okay, whatever. It's fine if you don't pick that up here. Now, later in the year, we will be doing the Pythagorean theorem formally, and you've got to pick up the Pythagorean theorem. But it's really not hard. You just need some practice with it. And then we can check if we did this right by grabbing all corresponding linear lengths, right, edges, and checking the copy compared to the original. All of those divisions should come out to be exactly the same, and they should all come out to be 1/2, or like 50%. Any questions on this? I should be capturing since I'm working down here. Choose your scale factor. I'm going to copy this out to my graph paper so we can do whatever scale factor we want. Choose your scale factor with this original shape. So it's got 1, 2, 3, 4, 5, 6 up, and then 3 across the bottom. Sometimes my dock camera looks like abstract art. They're like, I don't know, random thoughts from Hudson.
I love them.
Well, my buddy took a photography class in college, and he was rushing to get a project done. Actually, my buddy Randy, I'll be telling a lot of stories about Randy this year once we get closer into architecture stuff. So he was rushing to get this project done. Don't wait till the last minute, guys. And he was just finding stuff around the house to take pictures of. So he dumped out a bottle of like multivitamins on the counter and like set his camera to a weird apparition or whatever it's called, how much light you let in. And he got like really cool pictures of just like a pile of pills. And it looks kind of weird, but it's like pushing the idea of like, are drugs a good thing? Are they a bad thing? So it was interesting. 1, 2, 3, 4, 5. And it was a bunch of multivitamins, which like you don't know by the picture, but 1, 2, 3. You as a group decide if you're going to get bigger, smaller, what you're going to do to this.
50%, that should be really hard, so let's do it. Wait, we're supposed to already have it, and it's so
Then if you have it drawn on your paper and you want to come draw it up here, stick up a hand. Is it drawn on your paper?
Yeah. What are we even drawing?
Okay, that's what I said first. Now what's your scale guide? You guys play it.
Rochambeau?
No.
I know, right? It's harder to find your middle.
And it's also hard because it's just on the box.
Green doesn't really work. Yeah.
Black.
You can change your color up top if you want. Draw it, and then we'll get everyone's.
I'll tell her that my lines aren't straight at all.
We'll talk about that in just a second. It is on the dots, actually. Just not the line, but the end points are on the dots. But it doesn't matter. I'll show you how in just a second. I like if you want to see that. So what scale factor did Quinn use? Well, he went a little too far, but what scale factor did Quinn use? 50% and or if you use the fraction. 1/2. Now, I don't like that they give you scale factors and percents to begin with. You don't need to talk about scale factors and percentages. You can just use scale factor of 2, scale factor of 3, scale factor of 1/2. The length of the... All right, so this is really interesting, worth talking about because you guys are you guys. Thank you very much, Quinn. We can make this bigger, obviously, and then multiply everything out. But the question I'm getting from a lot of you guys is, wait, what about this length right here? It's not hard. And, like, I'm hoping that by a little bit of me peppering this in as we go, peppering in is like an expression for, like, it's not the whole dish, right? But I'm just going to toss a little bit in. Make a right triangle. 2, 3. And I could do this on the outside if you don't want to mess with your thing. 2 and 3. What's 2 squared?
2 squared is
4. What's 3 squared? Just shout it out. Ooh, 9. Be careful. 3 times 3. What is 4 and 9 together?
13.
So this length is the square root of 13. A bad number. An ugly, gross monster of a number. Let me make sure there's nothing else that I need to cover in the chapter. I think, or in the lesson. I think mainly it's scale factor, dilation, and the corresponding parts. Yeah, then we just determine what the scale factor is. So I'm going from 2 to 4. Oh my gosh. So we're pretty good. All right, so square roots and the Pythagorean theorem. Since we started talking about it today, and certain right triangles are similar and certain right triangles aren't. When we start talking about square roots and square ring, the reason that we know things aren't good square roots is because when I square these numbers, I get out my perfect squares. So 2 squared is 2 times 2. 4 is a perfect square. 3 squared, 3 times 3, 9 is a perfect square. 16, 25, 36, 49, and we can keep going. what I know when I get the result of radical 13 is that it's in here. Now, I want to blow your mind real quick for a moment. So everyone just write down these first 3 perfect squares. Well, 1 squared is 1, so it doesn't really count. So put down at least 2 squared, 3 squared, 4 squared. And then exactly like I have, put an arrow to your radical 13 being between 9 and 16. Oh, I love this. This is called the Rachel method. Rachel Shaw, and I should really email her this video and tell her, like, hey, look for the timestamp of like 35 minutes. Rachel Shaw was a student of mine years ago, and she came to me when we were working radicals, and this was back before CPM. She goes, Mr. Hudson, I have a strategy I want to try out with you. I said, okay, go. I love new math strategies. I love things I haven't seen. So she said, so you know, like radical 13, and I'll just use this for our problem. Well, we know that it's at least 9 because we know that it's at least 3 because my number in here is bigger than 9 and smaller than 16, right? So it's got to be between 3 and 4. I was like, okay, that's good. Like, yeah, that's a good strategy. She said, so check it. We want a decimal, right? But before we go to a decimal, fractions are better, right? My opinion, and I think was also Rachel's opinion. So she said, if we think about fractions, fractions are just talking about portions, right? And if we think about the number line, the square root of 13 is somewhere in here because it's bigger than 3 and less than 4. So the gap, and you don't have to understand this right now, but the gap between these perfect squares is 7. And the number 13 has bridged or gone through 4 of those numbers of like 9, 10, 11, 12, 13. It's 4 of the 7 to get there. This is very, very close. It's not exact. So actually, I would need to technically put a squiggly equals, but check it. This is like, you're going to have to clean up the brain. Go get the mop. The radical of 13, someone write this down so we have it written down. The radical of 13, syntax error.
I love them.
Are you kidding?
Yes, I am.
It's in math mode and it's giving me radical 13 is the radical of 13. Okay, it's 3.605. Like, and it goes on. Like, it's got other, like, but we don't care about that. 4/7. So, sorry, we'll write this down. 3.605. 4/7 comes out to be 3.571. So it is less than a tenth. Oh, it is 34 hundredths away from the exact answer. It is only 34 hundredths away from the. Now, not like there's more decimal places out there, but it's a very close approximation. It's not perfect, but it's a really cool, interesting strategy. And that works better, actually, as we get bigger. So I'm pushing time a little bit. Would somebody give me, let's just pick a radical between 36 and 40, square root of 40?
37.
37 is really close. Let's try it. We'll do 41. We'll make it a bit more funky. Square root of 41 is at least 6, right? Then what's the gap between 36 and 49? Total distance of 13, right? Yeah. And then from 36 up to 41, 5 of them, right? Square root of 41 is 6.403. The 5/13 gives us 383. Very close. Not perfect, like the 6 point, but very close. So it's just an interesting like strategy that she used. It only kind of works, but it's cool. All right, have a great day, guys. Oh, thank you very much.